Hello everyone, welcome to our channel Everyday E-Learning. In today's video we are going to learn how to implement a Boolean function using multiplexers. So for this kind of problems we will be given a particular function which may be in terms of min terms or max terms, and we'll have to implement that using a multiplexer or more than one multiplexer. Now for instance we are given the following function to implement, and it is given in min terms. So we know that min terms evaluate 1. So at these positions, that is at 2, 3, 4, 6, the value of the function will be equal to 1. Alright, so that is not very much required here. Just a recap, if you did not see the video of min terms from our channel, please go back and see that, as that will be useful in every topic of digital logic design. So let me get that erased. Alright, so at first we'll have to draw the truth table. Let's take the truth table first before we move on to the multiplexer part. So here we are given the min terms, and then we have A, B, C, and then we have F. So there are 3 variables. That means that this is a 3-bit, so there will be from 0 to 3, 4, 5, 6 and 7. Alright, so we'll have to denote it using binary for this 3-bit system. So it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Alright, so we are given that for 2, 3, 4 and 6 the min term value will be 1, because we can see that the summation is given, and we, as we told before, that the min term always evaluates 1. So when there we have 2, it will be 1, for 3 it will be 1, for 4 it will be 1, and for 6 it will be 1, and rest of the positions will be filled with 0. Alright, so now is the fun part. We can see, as we need to design the multiplexer or draw the multiplexer circuit, before that we need to do something. So for the first one here we can observe that BC equals to 0, 0. So if both of these are same, and this is also the case for this one, we can see that F, when B and C are same, follows A. Okay, let me take a different color for your understanding. When B and C have the same value, as you can also see here, B and C have the same value and the value is equals to 0, we can see that F follows A. F follows A. So we can write here as F equals to A. Now for a different case, when B and C, let me use that let me use a different color pen. If we see B and C when it is equal to 0 and 1, when B and C is equals to 0 and 1, then F here is found to be 0, and here it is also found to be 0. So when BC equals to 0 and 1, F is equals to always 0 for all the cases. Now if we see the next case where B and C is 1 and 0, we can see that it is for this one. Okay, let me again change the color for your better understanding. It is 1 and 0. Okay, very thick color. 1 and 0, 1 and 0. So we can find that F for 1 and 0 is equal to 1. Now if we get to the last one where BC equal to 1, 1, we can see that for this one we have BC equal to 1, and for this one we have B and C both equal to 1. So in that case we can see that the value of F is always opposite to that of A. Same for here. So we can write here that F equals to A bar. So we have the logic here, and we can use that logic to draw or design our multiplexer. So let me move down a bit. So we have 4 inputs here, so we'll need a 4:1 multiplexer. 4:1 mux. It will have a single output Y and 4 input lines along with 2 selector lines. So we can find that the first input is A, the second one 0, third one 1, and the fourth one is A naught, and the selector lines are C and B. This is selector line 0 and this is selector line 1, and this is our output. Now you might wonder why the selector lines are C and B. Since we have made the assumption or determined the value of F by observing B and C, and the value of B and C are determining which of the input lines are we going to direct to the output. That is why C and B are considered as the selector lines. Since B is before, we denote that as S0 and this one as S1. I hope you understood. That's it for this video. If you have any confusion, feel free to write down below. Thank you very much.